Hi, and welcome to this talk titled From Theoretical Computer Science to Learning Theory, which is an extended version of my MFCS 2024 invited talk with the same title. So what's the purpose of this talk? The purpose of this talk or goals, if you would say, is to first, I guess, introduce basic learning theory questions to a general theoretical computer science audience. And I want to argue in this talk also that the skills that we have from theoretical computer science, or TCS, are very useful also in studying learning theory. And hopefully this can also convince you to work on learning theory questions. I guess you could say that learning theory is part of theoretical computer science, but I actually believe there's been less overlap between the fields than perhaps there should have been. And the way this talk is structured is I'll try to argue all of this by basically telling you a personal story about how I got into learning theory, and I have a theoretical computer science background myself. Along the way, I'll give simple proof sketches for different results of mine that kind of demonstrate how TCX techniques have been useful in learning theory. And these results that I'm showing you are not necessarily my strongest results. Actually, they're definitely not my strongest results in learning theory, but I think they clearly demonstrate how TCS skills have been useful, and the proofs are also kind of intuitive in many settings. Right. So, before we start, because this video is mainly addressed to a theoretical computer science audience, maybe without any learning theory background, I want to just give a quick introduction to the basics of learning theory. Okay, so throughout this talk, we'll be looking at supervised learning, in particular binary classification. Right? So it's a simple setup. There's some input. It could be training images of cats and croissants. So they have labels here. It's binary classification, so the two labels, cats and croissants. And then we have some features that describe the input, for instance, all the pixels in an image. And now we have to use this training data somehow to train a classifier so that when we get a new picture without the label, so we see the features here, we can predict the label. Is this a picture of a cat or is it a picture of a croissant? Okay. A little bit more formally, just to introduce the basic notation that we'll be using, we say that data comes from an input domain X. X could be all images of a particular size. And the data has labels coming from an output domain Y. Cats, croissants, or typically we say -1 and 1 in binary classification. We interpret our labels as -1s and 1s. And then there's this unknown target function, which is the function we're trying to learn. So intuitively, this function should be thought of as the correct mapping of images to whether it's an image of a cat or a croissant. Of course, there are extensions to this model where f is not a deterministic target, a deterministic function that directly maps input elements to labels. But for this talk, it'll just be some function that correctly assigns label, and this is what we're trying to learn. Now, the training data that we have available consists of labeled examples, n of them. And each of these examples is an element xi from the input domain, and then the corresponding label f of xi. Okay, and the goal is then to train a classifier to produce a function f mapping, sorry, this should say that produce a function h mapping from the input domain to the output domain so that h looks like the unknown target function f. Okay, so we want to approximate the unknown target function. And what do we really mean here? So basically, these are the different ingredients in supervised learning here. There's an unknown target function f that we're trying to learn. We get these training examples. They're fed into a so-called learning algorithm A. A somehow, and we haven't talked about it yet, searches through a hypothesis set H to produce a hypothesis H that hopefully looks like this unknown target function F. So here, F again could be the mapping of images to cats and croissants. The training examples could then be a set of labeled examples. A typical learning algorithm, a normal strategy in machine learning, is to look for a hypothesis in the hypothesis set that correctly classifies a lot of the training data, right? Because on the training data, we can just check on each of the training items. We can compute what our hypothesis H thinks the label should be, and we know what the true label is. So we find such an H, and then we output that as our hypothesis and hope it looks like the unknown target function. Of course, I haven't talked about what is a hypothesis set H here, so we'll try to look at an example. And secondly, what do we really mean when we say that this hypothesis we produce looks like the unknown target function f? Okay, so hypothesis set first. So throughout this talk, we'll work with a simple example where we're looking at so-called linear models, right? So we're still stuck into binary classification, right? The output labels are -1 and 1. Here we say that the input domain is RD. So every input element, every input data point is described by D numbers, real numbers. Our hypothesis set now is the set of all hyperplanes. So for a hyperplane, we say that everything on one side is classified as -1 and everything on the other side is classified as +1. So here red illustrates the label -1 and blue illustrates the label +1. And all the triangles and circles are training data items. Okay. So secondly, we have this other ingredient that kind of allows us to say what we really mean by our hypothesis that we compute looking like the unknown target function. And this model that we'll be looking at here is PAC learning. So PAC stands for probably approximately correct and date back to the 80s. This model also tells us something about new data being similar to training data. And the extra ingredient that we need is a so-called data distribution. Okay, so one more ingredient in the whole setup is that there's an unknown distribution D over the input domain X. And the assumption now is that the training data that we have available, these n samples, are obtained by sampling each of the xi's IID from the distribution D, and then we just see, of course, the corresponding label f of xi. And the second assumption is that the new data that we need to make predictions on also comes from this unknown distribution D. And the goal now is to produce a hypothesis H with as small error as possible. And the error is just defined as the probability of mispredicting the label. And here we say that X now, this X in the probability is drawn from this distribution D. Okay, so if I get a fresh data point from the distribution D, the goal is to predict its label correctly with as high probability as possible. So this is kind of the extra ingredient that we add to this picture of supervised learning. There is this input distribution here that generates the xi's for the training data and also generates an x that we need to make a prediction on. And the hope is just that this hypothesis H that we produce, its error is as close to 0 as possible. Now, of course, you could ask yourself, is it always possible to obtain an error that's close to 0? And of course it's not. Let's say that you're training one of these binary classifiers by finding a good hyperplane, right? So you're trying to compute a hyperplane and to try and make predictions. So your hypothesis is the set of all possible hyperplanes, and there is this unknown target function f that just maps the input domain to the output domain. In this picture here, the input domain is, say, this square here, and you can see all the red part of the square is where the label is supposed to be -1, where f assigns labels of -1, and the blue is where f assigns a label of +1. And as you can see, there's no hyperplane that accurately describes f in this case. So there's no real good hyperplane in this setup, right? So what do you do? And like basically there are two different setups that you study PAC learning in. The simplest one is realizable PAC learning. So in the realizable PAC learning, we actually we make an extra assumption and say, well, the actual target we're trying to learn actually lies in this hypothesis set. So there is a hyperplane that has 0 error on all future data. There's a hyperplane that precisely describes what should the labels be of data points. The goal now in this setup is to output a hypothesis whose error is at most epsilon, right? So you want something that's really good. Could maybe be seen in this picture here. You have some training data, the red and the blue triangles and points. F is the true way labels should be assigned, and H is something that actually is correct on all the training data. You can see that all red points are on one side, all the blue points are on the other side, but it doesn't perfectly agree with this unknown target function F. So maybe on future data points, if it falls in between the two hyperplanes, we might still mispredict. But here, you can actually hope to get an error that gets arbitrarily small. The other setup is so-called agnostic PAC learning. Right, so here, what we say is that, well, I have already chosen my hypothesis set, for instance, the set of linear models. Right? This also holds if like your hypothesis set could be like all neural networks of particular architecture or whatever. But here, there's some H star in your hypothesis set whose error is the smallest possible under this distribution D among all hypotheses in H. And now the goal is instead to produce a hypothesis H whose error is not much worse than the error of H star. So it's only additive epsilon worse than the error of H star. Right, so this is called agnostic pack learning. Now, in both cases, probably the simplest learning algorithm you can imagine is called empirical risk minimization. Yeah, so what does it do? So we receive n training examples, right? So x1 to xn with labels f of x1 to f of xn. So it could be the ones in the picture here. And what you then do is that you just find a hypothesis in your hypothesis set who has the smallest error on the training data. So the error on the training data is just the fraction of mistakes that this hypothesis H is making on my training data set. So you just go for the one that looks best on the training data, right? So it could be this one here in the picture, right? This is my H. It perfectly actually classifies this training data set here, right? Because all the blue points on one side of the hyperplane, all the red ones are on another side. But you can see it's error under the distribution F, like under the distribution D that's kind of uniform on the square would be much higher because well, there's all this blue region on the right-hand side of the hyperplane, there's a red region on the left-hand side. Right. So in particular, this hypothesis that you find, it might not be the optimal hypothesis H star, right? So maybe the optimal hypothesis H star is this one here, like it is this second line. So this is the optimal H star is the one that has the smallest error under the distribution D, right? And you find the one, and you output the one that has the smallest error on the training data set. Okay. But maybe one can, as a first kind of example of just how can we use learning theory, what can we do? Can we prove that empirical risk minimization is a good strategy? Is it a good algorithm? And so let's, just to keep things simple, focus on when the hypothesis set H that we're searching through is finite. Okay, so it's definitely everything's simpler in the setup, but you can generalize it to infinite hypothesis sets as well. So let's say all these purple half spaces here are or hyperplanes are the only ones you're allowed to choose from in your learning algorithm. So what you do now, let's try to just fix one of them. Let's zoom in on one. So let's say this one here. And you can then look at what is its expected error on the training data set S. So expectation here is over the choice of the training data set. Well, since this is a fixed hypothesis, it has some error under the distribution D. And every time I get a training data set, it is drawn from this distribution, which means that the expected error of this hyperplane is exactly the error of this hyperplane under the distribution. The expected error on the training data set is equal to the error under the distribution D, because the independent, H is chosen independently of the training data set. Right. Moreover, the actual error on this training data set is an average of n, I guess, independent indicators that just say whether the ith training data point is misclassified. All of these indicators are independent, and their expectation is the error of this hyperplane under the distribution D. Okay. And so when you get each of these training data points, right, they follow the distribution D, and the error that you have on this little training data set is strongly concentrated around its expectation. In particular, you could use, for instance, Refuting's inequality to say, well, under my data, the probability over my data set S that the error on the training data set, so the empirical error, what I see on the training data set, and the actual error of this hypothesis, the chance that these two are more than epsilon apart is no more than 2 times exponential of -2 epsilon squared n. So it's just using Refuting's inequality because everything is independent. And what you can do now, at least for finite hypothesis sets, is that you can now do a union bound, as we're used to in theoretical computer science, right? Union bound over all the possible hypotheses and conclude, well, the probability over a training data set that there even exists a single hypothesis whose error on the training data set is much different than its error under the distribution D, and here much different means that they're more than epsilon apart, is no more than 2 times the size of the hypothesis sets times exponentially small in 2 epsilon squared n. So this allows us to kind of show that all our hypotheses simultaneously, the performance in the training data set and on new data is close. So if we look at that formula, play around with it a little bit, you get a conclusion like the following, right? So this is basically follows just by inserting this choice of epsilon into this formula. So what you get is that, well, if you look at an epsilon who's about the square root of log of the hypothesis set size over delta divided by n, then with probability 1 minus delta, it holds that every single hypothesis in the hypothesis set has an error on the training data set and under the real distribution D who are within epsilon of one another. Right, so this just follows by inserting into this formula and seeing that the right-hand side becomes at most delta. Okay. So it basically says that almost all the time, the performance of every single hypothesis on the training data set is close to its true accuracy on the distribution D. Okay. So what do we have now? We actually have a conclusion about this algorithm, empirical risk minimization. So what it does is, with probability 1 minus delta over the training data set, so that's the random part, this algorithm is going to output a hypothesis whose error under the distribution D, this is what we cared about, well, that error under the distribution D is within epsilon of its error on the training data set S, right? So the error of D, the error of H under D is at most the error of S on of H under the training data set plus epsilon. Secondly, since we chose the hypothesis with the smallest error on the training data set, that was the empirical risk minimization part. We know that the error of H on the training data set is no more than the error of the optimal hypothesis H star on the training data set. So now the error of H on the distribution D is at most the error of the optimal hypothesis on the training data set plus epsilon. And then we can again use this guarantee above that every single hypothesis, the error of that hypothesis on the training data set and the real distribution is within epsilon. So now we have related the error of our H on the data distribution to the error of the optimal hypothesis on the data distribution and shown that it's at most 2 epsilon worse. Right. So this is how you can argue that empirical risk minimization is a good strategy, at least when you have a finite hypothesis set. Okay. So what are the consequences of a proof like this? So basically, you can show that, well, if I have a finite hypothesis set, then empirical risk minimization returns with probability 1 minus delta a hypothesis whose epsilon, so the additive amount worse that you are compared to the optimal hypothesis of about the square root of log size of H divided by delta over n. Similar arguments, you can use the similar argument in the realizable case, just using here that there's always a hypothesis who has an error of 0, in particular the unknown target function has an error of 0 and it lies in the hypothesis set H by assumption. So if you're a little bit more careful, you get rid of the square root and you could get that the error is at most a log H over delta divided by n. And here it's important to note that these are probabilities, these are numbers less than 1. So the square root is actually a larger number than without the square root. Right? So that's important here. So this is a better guarantee. Okay. Right, so that was, I guess, the basics of learning theory. Now let us try to take a step, jump to some theoretical computer science background, and I'll try to give some, some background that we can use to prove something interesting in learning theory. Okay, so the first kind of thing we'll try to use is a very common or very famous result in, I guess, theoretical computer science, maybe in mathematics as well, the Johnson-Lillenstrauss lemma. So this relates to dimensionality reduction sketching. And basically the main result is that if I have n data points in d dimensions, then there's a way to embed or map these points to k dimensions, where k is just 1 over epsilon squared log n. So epsilon here is a precision that you choose, so that all the pairwise distances between these data points are preserved to within a factor 1 plus minus epsilon. Right, so basically, maybe you can project them onto this line here. You get a one-dimensional data set, and what you would like is that the distances between 2 data points are roughly preserved, right? So at least these 2 data points have their distance roughly preserved. Not all the data points in that picture have the distance preserved, but also this is a one-dimensional example. You need 1 epsilon squared log n dimensions to have a guarantee like this. The phrasing, I'll use a different phrasing of the result for this particular kind of talk, and that is that a different way of stating the Johnson-Lillenstrauss lemma is that if I have n unit vectors in d dimensions, then I can map them to the same 1 over epsilon squared log in many dimensions. so that all pairwise inner products between these unit vectors are preserved to within additive epsilon, right? So this is a corollary of the previous guarantee that is kind of easy to show. But this is showing, so here I'm not going to care about having the distances preserved. Here I'm going to care about having the inner products preserved. And I'm going to do it for under the assumption that my data points are unit vectors, or at most unit vectors. Right? And this is still a guarantee by this Johnson-Lindstrauss transform. Now, a result that I was involved in long ago, even before really venturing into learning theory, was can we prove a lower bound stating that on this number of dimensions that are necessary in order to preserve all pairwise inner products to additive epsilon. Right. So here, I guess, is a personal story of my own experiences. So when I started my PhD, I worked on data structures, like data structure upper bounds in particular. And I looked at questions like the following, right? So let's say you have a database of cars, and for each of them you have a price, and you have a number of kilometers they have already driven. And maybe you'd like to search in this database for a new car to buy. So a typical query, like basically an SQL type query, is list all the cars with a price from, say, 80,000 to 240,000 Danish kroner and a mileage of at most 120,000 kilometers. So this would correspond to reporting all the cars that falls within this rectangle here. Right. So this is a very classic data structure problem. And when I was working on data structures, one day I had a good colleague, a more senior PhD student, Alan Grenlund, came to my office in around 2009 with one of Mihai Petrascus's papers, and they're saying, wow, this stuff that he's doing here, these data structure lower bounds he's proving, that's so cool, and we really need to do the same. Sadly, Mihai Petrascu passed away just 3 years later. But this really kickstarted my work into data structure lower bounds. So many data structure lower bounds later, I guess I was invited to a communication complexity workshop in Banff. Here I am much younger and still with hair. And one of the other participants was Jelani Nelson, who's now at UC Berkeley. And he presented a nice open problem on Johnson-Lindstrauss transforms, exactly this, can you prove this dimensionality is optimal? And just this started a really long collaboration, and we still collaborate today. So what we set out to do was to try and prove that this number of dimensions is optimal. And I think one interesting thing that came out of it was that we can really transfer techniques from data structure lower bounds to the setup of maybe a more, I guess you'd call it geometric problem or dimensionality reduction sketching type question. Okay, so the main proof technique that we kind of used here was this notion of encoding proofs. And the reason why I'm going over this is both to show that maybe data structure techniques were useful in dimensionality reduction, and also we will see later that it's always this kind of transfer of techniques between different fields. So a very simple fact that we're kind of using in this proof is that it's not possible to give a lossless compression of, say, all bit strings of y bits into x bits for some x less than y. It's just a trivial fact that does not exist this magic compression box that allows you to take any long bit string and compress it into a shorter one and then uniquely recover the longer document, right? So this cannot happen. Basically, the idea is just there's not enough short strings to represent all the long strings. Right. So now the main idea in our proof of this Johnson-Lindstrauss lemma is to say, well, if I had a too good to be true dimensionality reduction algorithm, then I can compress a whole bunch of different inputs into something smaller and still get the input back afterwards, right? And now in the context of the Johnson-Lindstrauss lemma, the inputs that we want to encode are different carefully chosen point sets. Okay, so somehow we're going to feed in point sets, then we're going to do some kind of compression that uses a too good to be true dimensionality reduction technique to construct a very small representation of these point sets that allow us to recover the original point set. And so let's see how we do this. So we want to first construct a family of point sets, right? So this is the first part. What are the point sets that we will be compressing? So in our original proof, and I'll just try to give the high-level ideas, we have basically our point sets consist of two halves. The first halves are just standard unit vectors, E1 to En half. And here we're just, for simplicity, assuming the dimension is big enough that we can use these standard unit vectors as our input. Okay. Now, for the second half of our point set, we're going to look at a lot of different choices for these remaining points. And so let's try to be a little careful. So we're going to pick the remaining n-half points by picking n-half sets Si. Each of these sets are obtained by picking a subset of the standard unit vectors. In particular, the number of these standard unit vectors that we're picking is 1 over epsilon squared divided by 9. Okay, so we'll get back to why this is a good choice. And for each such, when we've chosen these sets of points, or these sets of unit vectors, standard unit vectors, we're going to construct a point set where each of these sets, Si, gives rise to a point or vector Vi. Now, what is Vi? Vi is obtained by saying, well, I'm just going to sum all these standard unit vectors that lies in my set Si, and I'm going to, let's say, scale them by 3 epsilon. Okay. So maybe it's easier to see in a picture. On the data set that I'm using here, here's one row for every point in my point set, and there's one column for every coordinate. Now, the first part of this point set, right, is just all the standard unit vectors. So they look like this, just ones on the diagonal. The latter half is obtained, again, it has a non-zero in every row for each of the standard unit vectors that is part of Si. Okay. And that non-zero is exactly 3 epsilon. Okay, so basically it's going to choose some entries and set them to 3 epsilon. The number of these non-zero entries is 1 over epsilon squared over 9. Now, one key observation here is that you can try and look at the inner products between these data points to recover these sets. Right? In particular, let's try to look at an inner product between one of the standard unit vectors EI and one of these vectors VJ, corresponding to a set SJ. As you can see, right, if EI is part of SJ, then the inner product is exactly 3 epsilon. If EI is not part of SJ, then the inner product is exactly 0. Okay, so it has this nice property here. Furthermore, the reason why we choose exactly 1 over epsilon squared divided by 9 many entries is that then all of these VIs are unit length vectors, right? That's the only property. We just get unit length vectors. Okay, so everything here in our input set is unit length vectors. Okay, now you can choose, okay, so how many point sets are there in this family of point sets we're considering? Well, what we have to choose is this last n-half data points. I guess the exponent here should have been n-half. But for each of these n-half sets, the number of choices of them, well, we have to choose 1 over epsilon squared divided by 9 points out of n-half points. So that's the number of different point sets in this big family of point sets that we're considering. Okay, so if now we want to kind of exploit this property of the Johnson-Strauss transform, we can take n unit vectors and then we can kind of map them to fewer dimensions while preserving all the pairwise inner products to within additive epsilon. So we want to prove a lower bound for this. And what we have now is we say, okay, our strategy is to say, okay, take any of these point sets in this family of point sets we just constructed or we just talked about. So each of these VIs corresponds to some sets. We're going to feed them into a too good to be true JL embedding into k dimensions for some k. And what the JL embedding guarantees is that, well, when I map them to k dimensions, all the pairwise inner products are preserved within additive epsilon, which has this important property. If we look at the key property they had before, it still means that if I look at the inner products between the embeddings of EI and the embeddings of SJ, we can still tell whether EI is a part of SJ because if it was, the inner product is larger than 2 epsilon. And if it wasn't, it's at most epsilon, right? So there's this gap between the inner products, right? We have one last step here because we need to turn things into bit strings and to use this encoding framework. And now the dimensionality reduction just produce real vectors. So we have one, like a randomized rounding step here. We can map these data points to a grid and use only order k bits per point to encode it. Okay, so really we get an encoding whose number of bits per data point is proportional to the number of dimensions that our JL embedding uses. Okay, and we can then this last step, this rounding to a grid, one can show that this only changes the mistake in the inner product to additive 1.1 epsilon instead of additive epsilon. Okay. So we now have this way of using O of k bits per point. And the nice thing about this encoding is that we can reconstruct the sets Sj from the encoding, right? Because the encoding tells us all these data points, they've been rounded to a grid. We know who they are. We know what these points are exactly from our bit description, which means we can compute inner products between them. And then we can just test, well, if the inner product is at most 1.1 epsilon between the encoding of EI and SJ, then EI is not part of SJ. If it is more than, or at least 1.9 epsilon, then we know that EI is in SJ, and this allows us to reconstruct the SJs and thereby reconstruct the point sets. Okay. But now we have this impossibility of compression, right? So this means that the number of bits we use in our encoding here, well, k bits per point, that gives like nk bits, order nk bits. And this needs to be enough to uniquely describe every point set, right? So it has to be omega log of the number of point sets in our family of point sets that we looked at. Number of point sets was, I guess it should have been n half in the exponent here. N half choose 1 epsilon squared over 9. And so the log of the number of point sets is basically, if you approximate the binomial coefficient, you basically get, and again, it should have been an n half here, you get an 1 over epsilon squared, you get a log epsilon squared n, right? So this is just approximating this binomial coefficient. So the lower bound really, and here the n half doesn't matter, you have nk has to be omega, so we anyways got rid of constant factors. Nk has to be omega n 1 over epsilon squared log epsilon squared n. So getting rid of the n factors on both sides, the lower bound is the number of dimensions k has to be 1 over epsilon squared log of epsilon squared n. And comparing this to the upper bound, this basically matches it, except when epsilon is really, really small. Like when epsilon drops to like 1 over root n, it's different. But other than that, it basically resolves the complexity of the Johnson-Lindström transform, right? So Jelani and I gave the first proof, and then very shortly after, and even at the same conference, Nogai Long and Boaz Klatak gave an alternative proof. Basically, the one I presented here is their version of the proof of the same result. Okay. So now I want to let's try and use some of this in learning theory. Okay, let's try to use some of these TCS results in learning theory. So let's go back to this picture here, right? So in learning theory, we're trying to explain often like, can we produce a hypothesis whose error is small? Right. So maybe one concrete example is, let's go to this realizable pack learning, right? So there is actually a hyperplane that perfectly classifies the data. And we're using, let's say, a linear model to try and make predictions in the future. So one problem with this is that there are actually infinitely many hyperplanes you could use. Like, so here I got a training data set of blue and red points. There are many hyperplanes I could use to classify it. And you could ask, are all hyperplanes equally good? So let's look at two different examples here, right? So let's say my training data set is the blue and the red points. These two different hyperplanes, I could use both of them for classification. Now, if you look at these green squares here in the picture, let's say that these are new data points I need to make predictions on. It could look, at least when we're looking at it, right, it seems that maybe the top green point should probably be classified as red, whereas the bottom green point should probably be classified as blue, maybe because they're sitting closer to, say, the red and the blue points. But now these two different hyperplanes that I drew here, they both classify the training data perfectly, but they give different predictions on the green and the green squares here. So it seems, at least just looking at the picture, that this hyperplane here is better than the other one, right? But why is that, right? The main reason is that it looks like it has so-called large margins to the training data, right? There's this big gap between it and the nearest data points of the two classes, right? So this is basically the intuition behind so-called support vector machine learning algorithm. In support vector machines, what you do is when you have a training data set, you use the hyperplane that has the largest margin to the training data, right? So use the hyperplane was this biggest gap to the nearest blue and red points, right? So here I'm just assuming that that there is such a hyperplane that separates the data. And I'm also, just for simplicity of this talk, going to assume that we're only going to consider hyperplanes that pass through the origin, right? So H passes through the origin, just to keep things simple, right? So let's say that let's look at the normal vector of this hyperplane W, right? So this is the one that's sitting here. So it's orthogonal to the hyperplane, pointing in the +1 direction. Now, a data point X, the distance of a point to this hyperplane is basically the inner product between X and W. But this inner product has a sign, so it's +1 on the side of the hyperplane that W is pointing, and it's negative in the other direction. So basically, you have a positive distance on the blue side of the hyperplane. These are all the x's with a positive inner product onto the normal vector. There's a negative inner product, or negative distance on the red side of the hyperplane. And the hyperplane itself is precisely described by the inner product between x and the normal vector being 0. That's the hyperplane. So the way that you typically write the prediction made by a hyperplane on a data point x is that you represent your hyperplane by this normal vector W, and your prediction is take the sign of the inner product between x and W, right? This gives exactly this classification that is shown here in the picture, right? Now, the margin now of a training sample is, so I have a training sample x comma f of x, so f of x is the label. The margin is take the signed distance from the hyperplane, so x inner product W, multiplied with the label f of x. And I guess here, as you'll see in this example here, well, if the data point indeed has a positive label, so it's blue, and it's on the blue side, then the inner product and the label have the same sign, and you get a positive margin. Similarly, if I have a red data point, it has a label of -1, and if it's on the red side of the hyperplane, then the inner product is also negative, and so the margin is positive, and it's equal to the distance that the distance from the hyperplane itself to the data point. So the margin is positive if the data point is classified correctly, and the value of the margin is how far on the right side of the hyperplane is it. If it's negative, it's how far on the wrong side of the hyperplane is it. Now, support vector machines now are just solving this optimization problem here, maximize the margin gamma here, subject to, so all margins have to be at least gamma, and the norm of this normal vector W has to be 1. There's a way to rewrite this optimization problem into something that you can solve, but this is what support vector machines does in the simple setup. So this really, support vector machines uses the separating hyperplane with the largest margin to the data. This is a super popular learning algorithm, and it's in all of these standard learning libraries like scikit-learn, and the original paper has like more than 50,000 citations. Now, if you want to ask a natural theory question here, is that, okay, can you give some theoretical justification for why would you choose a hyperplane with a large margin when you have multiple hyperplanes to choose from? Do large margins help in learning? Right. So maybe one first observation here is that these margins, they depend on the scaling of the data. In particular, right, because the margin is defined as the label times the inner product between the data vector x and the normal vector W. So if I scale the data vector by a factor x, factor c, then the inner product scales by a factor c, and the margin scales by a factor c. So in particular, like pre-scaling or scaling all my data by a factor c shouldn't really help in learning, right? It shouldn't make a difference whether I myself choose to blow up all the coordinates by a factor c. So to try and prove something interesting, and we're going to assume that all data points have at most unit norm. So they sit inside the unit ball. And you can always, and then we're going to try and make a theoretical statement in this setup. So the goal now is to show that if support vector machines returns a hyperplane with a large margin of gamma, then this SVM should have a high accuracy on new data, right? So it should be unlikely that it misclassifies new data. Okay. Now, how could we try and prove this, right? So maybe we could try and use this idea from, remember the warm-up where we introduced learning theory, where we did a union bound over finitely many hyperplanes. Can we try to reuse this idea to try and prove something here. Now, the problem is that there are really infinitely many large margin hyperplanes. Even if you insist on a large margin, there are infinitely many of them, right? So what we have to try and do is to, say, discretize all large margin hyperplanes into a small set that we can then union bound over. Okay, so let's try and see how could we do that. And here, the key idea is that, well, the margins are basically inner products multiplied with a label, right? In particular, it's the inner product. Probably they are actually inner products if you move the label inside, right? If you move the label, it's because of linearity, you can move it onto X here. And so the margin is really an inner product between a vector of norm at most a unit length vector and W, which is the normal vector of the hyperplane, which also is a unit length vector. And so we had this fact from before that Johnson-Lindner-Strauss preserves inner products. And what we're really using is actually the proof strategy for the lower bound that we had for Johnson-Lindner-Strauss transform. Because in that lower bound proof, what we showed was that you can basically take Johnson-Lindner-Strauss transform and you can use it to give a compression of inner products into some number of bits that depends on the precision epsilon, so the additive change in the inner products, and the number of data points n. Right, so basically we saw before that there's a way of taking a point set, doing a JL embedding and rounding it to a grid that allows us to use very few bits to approximate these original inner products. And so what is the intuition here? Well, the intuition is, in some sense, right, there's really not that many hyperplanes that actually matter. The only ones that actually matter are the ones that that these different encodings give us, right? So basically we said you can basically approximate and preserve all the inner products by mapping all of our data to this tiny grid that we can describe by B of epsilon n many bits. So really the number of different relevant hyperplanes to consider in some sense is only 2 to the number of bits that we use for compression. So let's try. So basically we can think of this proof that was in proof for JL is basically as a discretization. And this basically reduces it to only finitely many relevant hyperplanes that we could then perhaps union bound over. So let's see. So this was again the statement in the Johnson-Lindner-Strauss lemma, right? We can have n unit vectors in RD, the upper bound of JL, right? This is not the lower bound, this is the upper bound. Upper bound says you can map these points into 1 epsilon squared log n many dimensions while preserving all inner products to within additive epsilon. If we combine this with the proof strategy in the lower bound proof, what we actually have is that given n unit vectors, there's a mapping into a grid of 2 to the O of k many grid points, where k is just 1 epsilon squared log n, so that all the pairwise inner products are preserved to within additive epsilon. Okay. Now, if we combine this with SVM, what do we get? What we get is, so let's try and basically say use the JL embedding with epsilon set to around gamma or maybe gamma half. Then what we get is basically that we can take endpoints of, so say the training data set they all have at most unit norm. We can now map them into a grid of just size 2 to the O of k. K now is 1 over gamma squared log n. And now, if our hyperplane W that we had, if its margin was at least gamma, and the normal vector was W, then after this embedding, if we apply this M, say to our data points and our hyperplane, then we get that the inner products, they don't change much, which means that the inner products are basically what they were before the embedding, minus, say, gamma. Right, so or maybe gamma half if we choose our epsilon in the JL embedding to be gamma half, which means that, well, the sign of the inner product doesn't change, which means that if it had a positive margin before of gamma, it still has a positive margin, which means it's still correctly classified by this compressed hyperplane. Right, so this is just morally the case, right? So this is just the overall idea. So basically our compression of, if we apply this compression to the normal vector of the hyperplane, then it in some sense gives a hyperplane that perfectly classifies the embedding of the training data. Okay. And actually, the important point is that this hyperplane, if we take our normal vector and compress it, then it belongs to a small set. It belongs to one of these grid points of at most 2 to the O of k grid points. Right. So basically, there's only 2 to the O of k relevant hyperplanes to consider when you have a training data set of endpoints. So what we can do now is, and that's what actually happens in the proof. Now, of course, I'm not doing all the details, but what we basically can do is now we can just take the normal bounds for realizable packed learning. The normal bounds was that if my unknown target function lies in H, I get an error that is just a log of the size of H over delta divided by n. And this is just plugging into the standard results on packed learning for a finite hypothesis set. And for our SVM, when the margin was gamma, we saw that we can basically use Johnson-Lindstrauss to reduce the number of relevant hypotheses or hyperplanes to just exponential in order 1 over gamma squared log n. So if we plug that in here, this log of h just becomes order 1 over gamma squared log n. And so this is the result of an ICML 2020 paper together with Alan Grandon and Lear Kama, where we show with probability 1 minus delta over n samples, any hyperplane with a margin of at least gamma has an error of at most log n over gamma squared n plus log 1 over delta over n. So this is just actually formalizing these ideas that we just did. Take the proof of JL, use it to discretize all the set of all relevant hyperplanes, and do a union bound over all of them. And this actually is quite interesting, improved over long-standing results for support vector machines, where I guess the previous result, one of them had an extra log on the first term, the other one had a square root on the second term, which is again is worse because the bounds, the numbers lie between 0 and 1. Right, so basically we improve over all of this using JL. Right. Okay. Now let me try and give you a different story, right? So if you want to maybe get into a new area like learning theory, the way I did it was I also started out teaching a course, right? So I thought I was kind of interested in doing learning theory, and I had mentioned it at the department that maybe I'd like to teach a machine learning course. And immediately after, my good colleague Gerd Brodel got me assigned to this course. And this is actually the first place I saw support vector machines and margins, right? So this is was actually the inspiration for looking at this problem. And actually, there's been several other results along the way that came out of teaching something and then trying to think about it theoretically afterwards and actually improving some stuff. Okay. Now let me get to another line of results. And here I need to introduce another kind of direction in theoretical computer science that is then the key to this second set of results. Okay, so also when I was working on data structures, we saw before this example where you want to maybe list all the cars that satisfy some search criteria. Maybe you could also count them, right? So this is also a standard range counting problem. Count how many cars has a price between, say, 80,000 to 140,000 and a mileage of at most 120,000. Right? So in this example, there are 3 such cars. And you can then ask yourself, well, if I have a data structure where I can insert new cars, I can delete cars, is there a limit on how fast we can search and update the data, right? So data structure lower bounds again. And here I had an old result at Fox 2011 that received the Best Student Paper Award that was on relating this range searching question to an area called discrepancy theory. Right. So let me try and explain this connection just at a high level. So in discrepancy theory, we typically also look at point sets often. And the goal is to try and color these points red and blue as evenly as possible, right? So you can try and color them like this. Question is, what do you mean by evenly? By evenly, you mean you have some set of ranges in mind, for instance, all the rectangles like in our data structure problem. And then you're looking at all these ranges. And for instance, this rectangle here, the difference between the number of red and blue points is 2. This range has a discrepancy of 2. And the goal is to say that all ranges should be colored as evenly as possible. So like the max difference is your measure of quality of your coloring of the discrepancy. And basically the connection in my paper from 2011 is that if it's not possible, if I have a point set where it's not possible to color them evenly red and blue, then it's not possible to build a fast range-searching data structure on this point set, right? And what this allowed was to say, well, this discrepancy theory had been studied for decades by mathematicians, and now you could translate all of their work into lower bounds for data structures, right? Because since then, discrepancy theory has been studied a lot by the TCS community. Right, so maybe let me just say a little bit more about this discrepancy minimization, just because it's going to be key in the next set of results. So the goal here is to color endpoint red and blue as evenly as possible with respect to a set of ranges R. R could be all axis-aligned rectangles, all half spaces, all balls, what have we. The discrepancy for coloring now is the max over all the ranges of the difference between the number of red and blue points inside the range. Okay, so how did I get into this? And see this connection between range searching, data structures, and discrepancy. So really, it came out of talking to two different visitors when I was a PhD student. Right. So first we had Jeff Phillips, who's now at Utah, was visiting the group, and he is a computation geometer amongst many things, and he explained to me some classic results by Beck-Fiala and how you can color points evenly when you're promised that every point belongs to a few ranges, right? So if it's not included in that many ranges. Okay, so this is just an interesting thing. It was very different than what I was working on in data structures. She just told me about this result. And then a couple of months later, Elad Verben, who was a postdoc in the group at the time, said, oh, maybe can you try and prove lower bounds for these range counting type questions? And in particular, this got me thinking that, well, if my data structure has fast updates, it basically means that any data point has to be stored in few memory locations. Otherwise, you don't have enough time to change all those memory locations, right? Also, if you want to answer queries quickly, you have to read few memory locations to do it. And this basically, in some sense, is equivalent to this Beck-Fiala setup, right? That every point is in few ranges. Here, every point is stored in few memory locations. So basically, you just translate these ranges into memory locations instead. And that is the high-level idea of the connection. If I have a fast data structure, I get somehow a way of putting my points into few ranges, then I can do a good coloring using the Beck-Fiala result, and that gave the lower bounds at a very high level. Right. So this again is this discrepancy problem, and you're looking at the maximum of all these ranges. Now, you could also view this type of problem as something with matrices, right? So let me try and give this matrix interpretation. Right. So let's say I have my set of points and I have my set of ranges, and I can define, I guess, the incidence matrix of this so-called, I guess, range space or set system as a matrix A. It has a row for every query range. It has a column for every data point. And for every row, you just store basically an indicator telling us which points are in which ranges, right? So every row corresponds to a range. So like this rectangle, every column corresponds to a point, and you just denote which points are in which ranges. Okay. And now the second observation is that let's try and interpret the colors red and blue as numbers -1 and 1, right? So if we do so, then we can think of a coloring as just a vector in -1, 1 to the n, where n is the number of columns in this matrix A. And the discrepancy now of a coloring is precisely, if I take A and multiply it with x, what do I get? In every row, I get the inner product between x and that indicator vector, which is just summing up a +1 for all the points that are colored blue in this range and a -1 for all the points that are colored red in this range. So the absolute, if I take the absolute value of this entry, it's the difference between red and blue. And so that is, and now if I'm looking at the infinity norm of AX, I'm just taking the largest absolute value of an entry. That is the largest discrepancy. So it's exactly equal to this discrepancy over here, right? So the discrepancy, really, you can look at it in this matrix view where you have a matrix A, you're looking for a -1, 1 vector such that A times X has all entries small. Okay, so this view will be useful in the following. So that's, I guess, a more general version of discrepancy minimization here. The input is basically just an m by n matrix A, and the goal is just to find a vector x. It's a -1, 1 vector with n entries, minimizing the infinity norm of AX. Right, so this is super well studied. And what is coming up next is try to give some applications of discrepancy minimization in learning theory that have come up in my work. So it just turns out to be very useful there as well. Okay, so let's try and see a second example of using theoretical computer science in learning theory. In particular, we're going to try and use this discrepancy minimization. Good. So back to learning theory, right? We have realizable pack learning, we have agnostic pack learning, where in one of them, the unknown target function is in the set. In agnostic pack learning, you're trying to be competitive with the best H star there is, right? Now, of course, you could say in this agnostic setup, maybe a problem is that, well, if the best one H star is not very good, then it doesn't seem that great to be to try and be competitive with the best one there is, right? So if H star errors like in a quarter of the cases, doing a quarter plus epsilon errors is not that great, right? So what else could you try and do, right? And so this kind of motivates another very central line of work in learning theory called weak to strong learning. So a weak learner is basically a classifier that does a little bit better than guessing, right? So binary classification, so its accuracy is a little bit higher than a half. A strong learner, on the other hand, is a classifier that if I give it enough training data, I can make my accuracy arbitrarily high, right? So my error can be made arbitrarily close to zero. Okay. Now, a very classic question dating back to the 80s and 90s is, if I have access to a weak learner, something that is a little bit better than guessing, can I use it to construct a strong learner? Right. For that, I guess you need a formal definition of a weak learner and a strong learner. So the formal definition of a gamma weak learner now is a learning algorithm that for any data distribution D, if I have enough samples, so M0 is some constant, if I have enough samples from the distribution, then I will get a hypothesis H whose error is at most a half minus gamma under this distribution, right? So it's better than guessing by an advantage of gamma. An epsilon delta strong learner, on the other hand, is such that for any data distribution D, if I have some number of samples, I get, okay, this would actually depend on delta as well. Given m of epsilon and delta samples from this distribution, return with probability 1 minus delta a hypothesis whose error is at most epsilon, right? So that you can drive the error down to epsilon. It's just the number of samples depend on this epsilon, right? And actually, classic results also from the 90s show that indeed it is possible to take such a weak learner and produce from it a strong learner, right? So adaboost is a very famous example of this that even received the Gödel Award. So let me just show you, what does adaboost do? So in adaboost, the main idea is to say, if I have a weak learner A, I want to run it multiple times on reweighed versions of my training data set to produce a bunch of hypotheses, right? So I'm going to get a hypothesis H1 to HT, one for each iteration. I'm going to compute some weights. And at the end of the day, I am going to combine all my hypotheses in a weighted majority vote. So what does this mean? It means that basically I sum up all their predictions with their weights. Remember, these predictions are minus ones or ones. And then I take the sign of it. So basically, this is the same as asking, is there a negative majority or a positive majority, right? So of course, there's some technical details that one needs to fill in, like how do we weigh the training data in each of these training rounds? And the idea is to put large weights on data that has been misclassified before and low weights on data that's correctly classified before. So I'll try to explain that in a little bit more detail. And the weights of these alphas that you choose are somehow depending on the accuracies of them. I think I'll try to visualize it in an example here. So let's say you're running adaboost, and your hypothesis set is the set of decision stumps. Okay, so what does it mean? Basically means it's a decision tree with you have one root and two leaves. You get to ask a question in the root which compares one of the coordinates of a data point to a fixed threshold, right? So either you say, is this coordinate larger than A or less than A? Depending on which of the two, you have to output a label. And so basically this corresponds visually. If my data has two coordinates, two features, then my hypothesis is basically anything that can be described by a vertical split or horizontal split, where I can return, say, blue and red on either side. So let's say I have a training data set like this. And you can see here that if I train a classifier that's either vertical or horizontal split, I'll not be able to get 100% accuracy on this training data set. So what would adaboost do? Well, first you will just kind of put a uniform weight on everything and train a classifier. So maybe this one is pretty good, right? It misclassifies 2 points, it misclassifies these 2 blue ones. What it does now is to put a larger weight on the misclassified points here and a smaller weight on the remaining points. So now this is my new reweight data set. I train a classifier to minimize the error that I make on this weighted data set. So it costs more to make a mistake on a big point than on a small point. Maybe in this example, I want to get these blue ones correct because they have a large weight. So maybe this split is the best one I can compute. Now I'm misclassifying these 3 red small points. I'm going to reweigh my data set again. I'm going to increase the weight of those that I got wrong and decrease the weight of everyone else. So now kind of these 2 blue ones and these 2 red ones have a kind of medium-sized weight, and the others have super small weights because they've been correctly classified every time. Now my data set, it looks like this, and I've trained to minimize kind of the weighted error. And so here it would make sense to do a horizontal split because there's a large weight on these 2 points and a small weight on those, a large weight on these points and small on everything else. So basically, if I run for these 3 iterations, I'll get these 3 classifiers here. And if you look at what adaboost is doing, it's computing some weights for them. It doesn't matter too much for now how, but it computes these weights, 0.69, 0.73, 1. The final classifier is this weighted majority vote that on a given X, it asks all these 3 hypotheses, what do you think the label should be? And it combines them via these weights. So if I see a data point in this region up here, you'll see that all 3 say blue. So my prediction is basically I get insert 1 in all of these 3. It's a positive number, so I output 1. Up here, the first classifier says -1, contributing -0.69, and the 2 others say +1, so there's still a blue majority. Up here, both of the first 2 say -1, the last one say +1. And here there's a negative majority, so I say -1. And if you continue this, you'll see that this weighted majority vote perfectly classifies this training data set that we have here. So this is adaboost. So basically one can ask, if you want to try and understand, is this a good algorithm, right? Can you prove something about the accuracy of what comes out of adaboost, right? Can you prove that it actually gives one of these strong learners? And so let's say you run adaboost and what you feed in is a gamma weak learner. And to try and prove that this algorithm is actually good, has a small error on new data, we'll have to basically use a version of margins similar to SVM, but just tailored to these voting classifiers instead, these majority votes. Right. So let's try to look at what is margin theory for voting classifiers, right? So a voting classifier, again, is a weighted majority vote. And we can talk about its margin. Its margin on a training point, x comma f of x, so f of x is the label again, the margin is a number between -1 and 1. And what is it? So it has this kind of complicated formula. So let's have a look at it. So as you can see here in the numerator, we have the label of the data point, and it's multiplied by basically the prediction that the voting classifier G would be making before taking the sign. Right, so this is just basically the prediction that it's making without the sign operation. So you multiply those 2 together, and finally you normalize by the sum of absolute values of these weights. Okay, so since we normalize by the sum of absolute values of the weights, each of these h's are outputting numbers between -1 and 1. The sum here, the value that G is taking before the sign operation, when we normalize by this denominator, is a number between -1 and 1, and we multiply it with a label that is a number in -1, 1, so we get a number between -1 and 1. Basically, this, if you basically think of it as this normalization term is just a scaling of all the alphas to so that they sum to at most 1. You can basically think of this as the weighted fraction of correct voters minus the weighted fraction of incorrect voters. In particular, if the alphas are non-negative, that's exactly what it is. Okay. So the margins are basically, if it's 1, it means that everyone is correct. If it's -1, it means everyone is wrong. If it's 0, it's half is correct, half is wrong. Right. So intuitively, large positive margins means that we are correct and very certain. Close to 0 means we're very uncertain about the predictions. Okay. Maybe let me just show an example here. So let's look at the margin of a voting classifier. So let's say we have this training data. We have 3 different linear models, like 2 different hyperplanes. And let's look at a majority vote of these hyperplanes where we put an equal weight on all of them, right? So we have these 3 hyperplanes. In each of these regions, 3 say blue, 2 blue, 1 red, and 3 red. I guess in here it's 1 blue, 2 red. I guess I'm missing a red here, and so forth. So if I have a data point up here, 3/3 are correct, 0/3 are wrong, so the margin is 1. In here, 2/3 are correct, 1/3 is wrong, so the margin is 1/3. Over here, 1/3 is correct, 2/3 are wrong, so the margin is minus 1/3. Okay. So if you want to try and analyze adaboost, one way to do it is to show, well, if I run adaboost with one of these gamma weak learners, and then after 1 over gamma squared log n iterations, all of the training data is classified correctly. And in particular, the margin that I have is some mu that's at least gamma half. And so it has a margin proportional to this gamma in the advantage. Now, similarly to the support vector machines, if let's say we have a base hypothesis set, so the one here, the vertical splits and the horizontal splits, if we have a base hypothesis set, let's for simplicity say it's finite, then we basically can prove a similar statement. With probability 1 minus delta over the training data, every voting classifier G, whose margins are at least mu, have an error of at most log of the size of H, log n over mu squared times n. And this can be proved basically via a discretization. Basically, you get a discretization again. Okay. So this is basically saying that, okay, if I have large margins, or if this advantage is good, if my gamma is good in my weak learner, so I have a good advantage, I run it for a long time until all my margins are high, then I can just invoke this kind of generalization result that says, well, all hypotheses that have good margin, every voting classifier with good margins, in particular the one that adaboost produces, also has a small error, right? So this is how it goes, right? You can show every voting classifier with high margins has a small error. Adaboost, if I run it for long enough, has high margins. Done. Okay. So large margins are good, basically by this generalization bound, as it's called. So we know that large margins are good. But of course, if you care a little bit about speed, if you try to make a prediction, whenever you have to predict the label of a new data point, you have to ask T different hypotheses, what do you think the label should be? And then do a majority vote. So this can be kind of slow if you have a large T. So a natural question to ask is, what is the trade-off between the number of hypotheses you combine and these margins that you can obtain? Right. In particular, let's say that the best achievable margin you could get if I'm allowed to combine as many hypotheses as I want. Okay. Let's say I can guarantee that all my data sets, all my data points in my training set have a margin of gamma star. Then you could ask, how many hypotheses T of epsilon do I need to combine to obtain a margin of at least gamma star minus epsilon? So get within additive epsilon of the best margin, right? So this is an interesting question you could ask. So basically it's relating to the runtime of this, right? So this has been studied before quite extensively. In particular, there's an algorithm by Retsch and Warmuth that shows you can actually get an epsilon that grows as the square root of log n over t. Right, so you can solve this for t to get log n over epsilon squared. Okay. And there's also a lower bound people that you can deduce that says that this is actually optimal, the trade-off between t and epsilon, as long as epsilon is not too small, if you don't want to get too close to optimal, right? So it's larger than n to the minus 1/4. And now there was in an old cold open problem write-up from 2013, Ni et al. Basically wrote it down as a conjecture that this is tied even for any epsilon down to 1 over square root n. Okay. So this was a nice open problem, and this was published as part of the Cold conferences publishes open problems. This is something that we looked at. In particular, in a result from ISTML 2019, together with a student, Alexander Mathiasen, and previous, now at this time, postdoc Alan Granlund, we basically refuted this conjecture. We showed it's false. And in particular, our algorithm is kind of interesting. And I think it's maybe not so much the result itself, but the algorithm is kind of cool. In particular, because our algorithm uses discrepancy minimization. I think this is quite surprising that this has connections in majority voting. So basically what we do is we say, well, you can run the previous algorithm by Refuting and warrant to get margins to within epsilon half of the optimal, right? So they're at least a gamma star minus epsilon half. You can do that by running for a log n over epsilon squared many steps, at least all of this. And now our idea is to now prune these hypotheses, throw away some of them while keeping all the margins basically the same. We want to say none of the margins change by more than epsilon half. And then, of course, our new margins are within epsilon of optimum. Right, so how can this be done? How can we prune or sparsify using discrepancy minimization? Right, so recall again, like the voting classifier that we have is the sign of such a sum here of alpha I hi, so a weighted majority vote. And for this, to keep things simple, let's say we've just normalized all these alphas so that the sum of absolute values of them is 1. Okay. Now, if you now look at a data point, like the one in here, the margin of on this data point is the label of that data point times the sum of these alpha i's hi of x. And this is because we made this assumption that everything has been normalized to 1. So this is kind of clean. So that's the margin on the data point. What we do now is we say we have a training data set, right? And now we construct a matrix from it. In particular, we have these hypotheses H1 to HT that we obtained by running the previous algorithm by Refuting and warrant. On each of the data points, we're going to construct a row. And what do we put in this row? In the entry of this row corresponding to a hypothesis hi, we basically write down the contribution of this hypothesis to the margin, right? So that contribution is f of x from over here, alpha I hi of x, right? That's the contribution to the sum. So let's put that into an entry of this matrix. Now, what is the observation is? The observation is if I sum all the entries of a row, then the value I get exactly equals the margin, just by definition. Okay. So what is our key idea now? I have this matrix. What do I want to do? It looks like discrepancy now. At least there's a matrix involved. Our idea is to say we want to prune this hypothesis set by selecting a subset of the columns, say at most t half of the columns. What we're going to do is we're going to upscale all the values in this column by a factor 2. And I'm going to set all columns outside s to 0. And while doing so, what I want to do is I want to approximately preserve all the row sums, because the row sums were really the margins. And what does this actually correspond to? Basically, it corresponds to saying, well, if I'm scaling up everything in a column by a factor 2, it just corresponds to updating all the alpha i's with I and S by a factor 2 and setting all alpha i's to 0 where I is not in S, which means I basically pruned away at least half of my hypotheses by scaling up the coefficients on the remaining hypotheses. And still, after this change, the row sums again equal the margins of these changed alpha i's. And then what I can do is just recurse to reduce t further just by another factor 2 and so on. Okay, so now how can we choose half of the columns to upscale by a factor 2 and downscale the rest to 0? And the way we're going to do it is we're going to take this matrix A that we just defined, and let's gonna find a low discrepancy coloring, find a -1, 1 vector that minimizes the infinity norm of AX. Now, why is this useful? Right? So let's try and think of it as we're coloring the columns. All the ones now with where xi is -1, we set to red, and all the ones where xi is 1, we set to blue. We have some observations now. Let's look at a row sum of this matrix, right? So the sum in a row is just the sum over all coefficients in the row, right? So the sum over j, aij. Of course, that splits into the sum also over those aij where xj is 1, plus the sum over all those j where xj is -1. That's a trivial observation. Okay. We can also look at what is an entry in the product AX. Well, the entry in the product AX, the ith entry is Well, it's the inner product between the ith row and the x vector. So it's the sum of all those j in the row where xj is 1, aij, minus the sum of all those entries in the row where xj is minus 1 of aij. Okay. Now I can basically add these two lines together, these two equations together. And what we get is that, well, if I add them together, the sum over the negative coefficients of xj disappear. So we get twice the sum over the positive coefficients. I could also subtract the second one from the first one, and then I get twice the sum over all entries where aij is negative. Okay. So what we could now do is, what we observe is, let's try and take we have our coloring X. What I want to do now is I want to take all entries of this matrix where xi is b and scale them up by a factor 2, and all where xi is minus b and set them to 0. So here, this holds regardless of whether I choose b equals 1 or b equals minus 1. If I do this, then these two observations mean that any row sum margin changes by, at most, the infinity norm of ax. So what we can now do is we say, well, there's at most half of the entries that are either minus 1 or 1. Like for one of the two, there's at most half the entries that are that value. So what I can do is just I just set those to. So basically, you can see it here, right, in this equation. Let's say there's fewest plus ones. Okay, the fewest plus ones, at most t half of them, I could set all entries with a plus 1 to scale them up by a factor 2 and set all the other entries to 0. Now, any row sum now is twice the sum of all the entries where xj is 1, aij. So it's this right-hand side here. Well, what that sum is now is equal to the original sum plus the ith entry in ax, which means I changed the row sum by at most this absolute value of axi. And which means that and this holds for every single row I, which means that no row is changed by more than the infinity norm of ax. Similarly, right, if there were fewest minus ones, I scale up all the entries that has a minus 1 in x by a factor 2, set all the others to 0. Now my row sum is the second one here. Like in the ith row, my sum is twice the sum over all the entries where xj is minus 1 of aij. And that is equal to the original row sum minus the ith entry in ax. The ith entry of ax in absolute value is at most the infinity norm of ax. So in this way, if I find this minus 1, 1 coloring, it allows me to preserve basically the row sums. So the way we refuted the conjecture now is that we could actually now use discrepancy minimization upper bounds to find a good minus 1, 1 vector here to do this recursive, to halve the number of hypotheses that are left. In particular, we use a famous result from 1985 by Spencer, known as Spencer's 6 standard deviations suffice. What we get is a different epsilon that grows as the square root of log of n over t divided by t. And basically what you can see is that as epsilon, if you set this towards 1 over square root n, this basically means that, or basically also you could see that as you let n or t goes towards n, you get log of n over n, so this goes away, and you get basically 1 over square root n epsilon here. Whereas the conjecture says that the t that you need has to be at least n log n up here. Right, so basically there's this gap between the two as epsilon becomes small, comes close to this boundary where it's a 1 over square root n. So when we get close to this boundary, our approach using Spencer's 6 standard deviation suffice basically shaves off this log n in the number of rounds t that you need. Okay. So here, discrepancy minimization was really useful for pruning a set of hypotheses in a voting classifier. Right. Okay, let me say a little bit about how this result came to be. Actually, this was my student, Alexander Mathiasen, was really interested in working on machine learning. And at the time, I hadn't really worked on it yet. And this was actually my first real learning theory result. And I think he realized that I was not too excited about doing very practical ML, particularly because I don't think I'm very good at it. There are many people out there that are much, much, much better. And I also feel like I had all these nice ideas and knowledge from TCS, and I really would have missed using many of those stimulating ideas. So I think he realized that I was like that too. So he looked for theory ML problems and came across this cold open problems list and actually found this exact open problem formulation and that we then addressed. And this is really like the cold open problem list is a great source for inspiration. Examples I prepared. So I tried to introduce some basic learning theory questions in the beginning, and then I tried to show here some examples that classic TCS skills are useful in learning theory, also saying something interesting, both NP hardness, discrepancy minimization, dimensionality reduction. I hope that this shows at least your techniques are also useful in learning theory and that there are some very interesting questions there. And I tried to base it on, I guess, my personal story. I tried to use simple proof sketches demonstrating TCS techniques in learning theory. Maybe there's a few other takeaways, maybe in particular to more junior researchers. I think be open to collaboration. I think as you might have seen, like many of these directions came to be through talking to other people in other seemingly unrelated fields. And TCX techniques are really often applicable in many different places, in addition to where they were invented. Teaching a course may be a really great way to get started in a new area. And for learning theory, I think looking at the cold open problems set is like maybe a really good starting place to begin with. At least for me, what worked really well was to try and start in one corner. So we had this first result about boosting, and we used discrepancy minimization, and then try and expand from there. So I had a lot of results that relates to boosting since then. With these margins led me to support vector machines and so on. So try to gain some expertise in the corner, and then you can expand from there. Right. So I hope you found this video interesting and inspiring, and I hope that maybe some of you will consider also working in learning theory. Thank you.